All right, so the two rows, or it might be 3 or 4 or 5, depending on the number of variables, the two rows to the far left are just the variables. Now we have a set of rows that will represent the premises in the argument. And let's say that I have a premise that is P or Q. That's one premise. I have another premise, and we'll say this other premise is not Q. Not Q. And then the conclusion of my argument is P. And over here I'm going to put my conclusion. This will be in the third section of the truth table. My conclusion here is P. Okay, now what I have to do is go back and look at these various rows and calculate the truth value of each one of the compounds or simple statement variables. And that's going to be done on the basis of the combinations laid out over here on the left-hand side of the truth table. And we've just spent some time learning how to do this. This is not hard. By the way, in the case of the conclusion line, since I don't have a compound, I just have one of the variables, then I can go through and fill in for each one of these lines what it is on the basis of what's already been assigned. So for line 1, it's going to be true. For line 2, true. For line 3, false. For line 4, false. Now, if I had a compound statement here, I would have to do, I'd have to look at this and evaluate it. It wouldn't be as automatic as that. For instance, here's a compound statement. Let's go through and do this premise. P or Q. Now, given that we have the assignment of truth values true and true, is the compound P or Q true? Yes, and all you need is one to be true, and so that whole compound is true. Now, if Q is true, so look at this next row, if Q is true, is not Q true? No, then it's false. Let's go down to the next line and consider this possibility of truth assignment, true and false. If I have P or Q, that is false or true, is the whole compound true? Yes, but there is at least one true component, so that isn't true. Now in the third line of this particular table, Q has been assigned a value of true, so what is not Q's value going to be? It's false. It's going to be false, that's right. And now we only have one more line to consider, the assignment of false and false to the variables P and Q. Now, if P is false and Q is false, then what's the compound P or Q going to be? False. It's going to be false. On this particular line in the chart, Q is said to be false. What is not Q going to be? True. True. Now we have finished the chart. It's completely done. We've looked at every possibility. I'm going to back up here. We've looked at the specific form of the argument. We've realized that the truth value of the compounds, we only have one here, can be determined by the parts. And now what we have to remember is an invalid argument is one that has true premises and a false conclusion. So the first thing we have to do is to go through that segment of the truth table that lists our premises to see where we have all true premises. Any line in a truth table that has a false premise can be excluded automatically, because the only thing we're testing is to see if we have true premises and a false conclusion. So we have to have all true premises. Of these lines on the truth table, where do we find all true premises? Which line?
Second line.
I'm sorry?
Second line.
The second line alone has all true premises. The rest have at least one false premise. So they won't help us determine validity or invalidity. In some truth tables, depending on what your premises are, you might have many more than one line. So don't think that in a truth table you're just looking for one line. You've got to check for every line that has all true premises. We only happen to have one there. Now in this particular case, where there are all true premises, is the conclusion also true?
Yes.
And therefore it is not an invalid argument. Now, if we had, on a different illustration, put this together in such a way that a false was found in the conclusion row on the line where you have all truths for premises, then you would have had true premises and a false conclusion as a logical possibility, and thus you would have to rule that form out, that specific form out, as an invalid argument. And does that help everyone understand how we use truth tables?
Will you ever have it, is it possible to have two true premises and a true conclusion, and then further down have two true premises and a false conclusion?
Yes, because what you're looking at are different possibilities. So you might have on a truth table, for instance, like this, in the premise rows, let's say we have three possibilities. You might have a false, a true, false, and true, a true, and true, a false, and true, a true, and true. Okay, now you're going to get different combinations depending on what the compounds are up here. But you might have one line that has true premises, but the conclusion of the argument turns out to be true here, but down here on this combination of different things, the conclusion proves to be false. Now when you have that, because of the different values assigned to the variables, then you know you have an invalid argument. Some forms of the argument will lead to the truth in the conclusion, but not all forms, and therefore the specific form is not reliable. It's not reliable because there's at least one way in which you can have true premises and a false conclusion. The author tells us on page 283 that a given argument can be a substitution instance of several different argument forms. And there is no reason, he says in the middle of the page, why an invalid argument form cannot have a valid argument as a substitution instance, but the specific form of a valid argument must be a valid argument form. On the other hand, a valid argument form can have only valid arguments as substitution instances. And so essentially what he's telling us here is that in terms of argument forms, if you have an invalid one, you might have, this is in a sense what I was just explaining to Pete, you might have some arguments that are valid arguments, but in other cases they are not. However, a valid argument form has only valid substitution instances. So, to prove that a given argument is invalid, we must prove that the specific form of that argument is invalid. That, by the way, explains why when I taught you the truth tables in the Dr. Bahnsen way, I began by saying, remember what invalid means? It will not be enough to test for validity in the sense that you only look at the argument possibilities where the conclusion is true. You must look for those where you have true premises and a false conclusion. That will tell you whether it's invalid. To prove that a given argument is invalid, we must prove that the specific form of that argument is invalid. Okay, let's do some exercises just to catch on to this. On page 285, Roman numeral 2, Kofi says, use truth tables to prove the validity or invalidity of each of the argument forms in group B above. So we have to go back to Roman numeral 1 and look at the group B argument forms. He says, use truth tables to prove the validity or invalidity of these. And let's begin with number 1. Okay, let me walk you through number 1 just as a way of refreshing what we've just learned about truth tables. Number 1 has as a premise, if P then Q. It has as a conclusion, therefore, if not Q, then not P. First thing we have to do with the truth tables, we have to get our variables. In this case, we only have 2 of them, P and Q. And how many possibilities will there be? 2 to the nth power, 2 to the second power, 2 to the 4. True and true, true and false and true, false and false. So those are my variable. Now, how many premises do I have in this argument? Just one, and that premise is if P, then Q. And then the conclusion is this compound statement, if not Q, then not P. And now I just have to figure out how to fill in the chart for the various possibilities. If P, then Q, where I have if true, then true, is true. Okay, if P, then Q, when I have true and false, is false. Everybody with me so far? That's what material implication is all about. Okay, if P, then Q, when I have a false antecedent, is true. When I have a false antecedent on the last line here, it's true. Okay, now let's fill in the truth value of the conclusion, which is a compound statement that says not Q, if not Q, then not P. Okay, on the first line, Q is true, so not Q becomes false. We know that a false statement applies to anything, so we can automatically put that down as true. On the second line, Q is false, so the not Q becomes true. Okay, if true, then not P. The P on this line is assigned true. Not P becomes false. Therefore, looking at the whole thing, you have if true, then false. So that's false. Now in line 3, Q is taken as true, and not Q, therefore, becomes false. And anything that is false implies anything, so we can automatically put that down as a true statement. And then in line 4, Q is false, not Q becomes true. P is assigned the value of false, not P therefore becomes true. And so what you have here is a true implying a true, and that is true. Now that we've got the chart filled in, all we have to do is look for all those lines that have true premises. In this case, there's only one premise, so it's pretty easy. We go down this column here, and we look at this, and this. Lines 1, 3, and 4. Now, do we have any that have true premises, any lines true premise, and a false conclusion? Here, line 1, the conclusion is true as well as the premise being true. In line 3, the premise is true, the conclusion is true. In line 4, the conclusion is true, and the premise is true. And so we don't ever have the combination of true premise and false conclusion, and thus we conclude this is a valid argument form. Everyone follow that? Okay. Then, Melissa, let's have you walk through the next one, number 3.
Okay. On the board. We've written down the different truth value combinations for the variables P and Q.
So we have 4 lines on this truth table.
Yes.
Okay.
And it says that the conclusion is P, therefore we can just look at our truth value combination and write down what the conclusion is from that.
Yeah, each line with respect to the conclusion is easy because that's just one of the variables itself. And of course we have to write it down in the same order that it's found over here, don't we? Okay.
And the premise is P and Q. So, if we know P is true, if we know P is true and Q is true, then the first premise is true. We need at least one. We need at least one to be true.
No, that is a disjunction. In the case of an and statement, conjunction, both have to be true in order for the compound to be true.
Okay. So in the second combination where P is true and Q is false, the premise has P and Q has to be false because both aren't true.
Right.
In the third where P is false and Q is true, the premise Q and Q has to be false because there has to be Q true. And in the final one where both P and Q are false and the truth value combination, the premise P and Q has to be false.
That's right. So now we have filled in the truth table completely. And the next step is to look for of the row or rows that have only true premises.
The first row.
That's the only one. Now, is the conclusion true or false on that row?
It's true.
So you have true premises and a true conclusion. That's the only possibility when you have true premises. Therefore,
It's a valid
the
argument.
argument is valid. Very good. Then let's, I think we're getting the hang of this, and I don't want to spend a great deal of class time doing what should become fairly mechanical. So let's just try one more. All right, we'll do number 11, and we'll have Jay walk us through it.
Okay, we got 3 variables, so we need 8 columns.
Very good.
And then I just went through and I figured out if P is in Q, and I filled out the table for all 8 columns. And I did the same thing for if P is in R, and the same thing for if Q, not if Q, Q or R. And in doing that, I found that on the very last column, very last line, you'll have 2 true premises and a false conclusion.
Okay, let's test that to see if you're right. Let's pretend that I didn't stay up late at night and work out all of those 8 rows. But I just kind of sat there and I played with this a minute and I said, well now, what if P, Q, and R were all false? Let's just take that as the assignment. And that's what you have in your last line. Now, if P, then Q, if false, then false, would turn out to be a true compound statement. And that's, you have that on your line. Now, the next premise is if P, then R, that is, if a false, then a false. Well, that's true as a compound statement. So both of the premises are true. Now, let's look at the conclusion. Q or R, where both are false, is false or false. At least one has to be true. So that compound statement becomes false. Consequently, we have a line on the chart where every premise is true, but the conclusion is false, and that is sufficient to prove invalidity. Any argument of this form that we find in number 11 will prove to be an invalid argument. Follow that? Very good. All right, we're going to move ahead and learn some more about symbolic logic in section 8.5 of Copy, beginning on page 286. Section 1 talks about statement forms and statements, but I'm not going to bother with it because, as he says, we now make explicit a notion tacitly assumed in the preceding section. That can be a little confusing. You think, well, I'm supposed to be learning something new. I mean, what's this all about? You think, well, in a sense, you already understood this if you did what you were required to do and understand in the previous section. So now let's go on to the notion of tautology, contradictory, and contingent statement forms, section 2 on page 287. In the middle of the page, Copy introduces a distinction between statements whose truth can be discovered only by observation, that is, only by empirical study, and statements whose truth can be known simply by their logical necessity. If I say, Washington was born in Spain, George Washington was born in Spain, there's nothing you can do to tell if that's true or false except empirical study of history, the facts of history. But if I say, it's either the case that Washington was born in Spain or he was not born in Spain, it doesn't make any difference what you know or don't know about history. That's logically true. One or the other of those is going to be true. Now then, he gives a definition of tautology that you can understand in light of what we have just learned. He says a statement form that has only true substitution instances is called a tautologous statement form, or a tautology. A tautology is a statement form where all the substitution instances are true instances. And it gives you a little truth table there to show you, in the case of P or not P, no matter how you assign the truth values to P and not P, the combination P or not P is always going to be true. So where you have a truth table, and that line has only truths in it, or that row, I should say, that row has only true in it, then you know you're dealing with a tautology. Okay? Now, on the top of page 288, he says a statement form that has only false substitution instances, that's the opposite of what we just learned, one where you have only F's in that row, is said to be self-contradictory, or a contradiction, and is logically false. So if you have all truths, you have a tautology. If you have all falses, you have a self-contradiction. Then the next paragraph says, statement forms that have both true and false statements among their substitution instances are called contingent statement forms. They might be true and they might be false. They're all false, they're self-contradictory. They're all true, they're tautological. And if they're true and false, then they're contingent. That shouldn't be all that difficult. Any problem? Then what do we mean when we use the expression material equivalence? In the middle of page 288, Kofi says, two statements are said to be materially equivalent, or I think it's easier to remember this expression, equivalent in truth value. Two statements are said to be materially equivalent when they are either both true or both false. When they are true together or false together, they are materially. Okay, so he gives a truth table here for P and Q. And he said, look at the lines where P is true and Q is true. And you notice that P, and we're using the triple line equation, material equivalent, P materially equivalent Q is true as well. Where both P and Q are false, P material equivalent Q is true. And the reason for that is the material equivalent sign simply means you have the same value on both sides of it. And if you have the same value, then the compound is itself true. Have I lost anybody? This asserts an equivalence, and so they either are equivalent or they aren't. If you have true and a false, they're not equivalent. So then the total, the compound, P materially equivalent Q, would not be true. Whenever two statements are materially equivalent, they materially imply each other. And so we can read the material equivalence sign, the three-line equation there, as if and only if. And in logic, that's called a biconditional. Both sides imply the other. If and only if amounts to if P then Q, and if Q then P. So now we know what a tautology is, a self-contradiction, and a contingent statement. We also know what material equivalence between two statements amounts to. Now, how is that different from logical equivalence? The author says at the very bottom of the page, two statements are logically equivalent when the statement of their material equivalence is a tautology. This is a recursive definition. You've already learned what material equivalence is. You've just learned what tautology is. And so when the statement of a material equivalence is a tautology, then you have a logical truth. So look at the truth table down below. He has P and not P and not P. And then he puts down the statement of the material equivalence of P and not P. That's the last row in this truth table. Now, is the statement of that material equivalence, the material equivalence is the three-lined equivalent sign. Is the statement of that material equivalence a tautology? Well, now you say, well, Dr. Bahnsen, a tautology is a statement where all of the values in the truth table for that row are true. And you look at this and say, well, all of them are for this one. So that material equivalence, that statement of material equivalence is a tautology. So we now have a new term for this P materially equivalent, not P. We call that a logical truth. A logical truth. A logical truth is one where the statement of a material equivalence is tautological. The difference between logical equivalence on the one hand and material equivalence on the other hand is very great and very important. He says logically equivalent statements have the same meaning and may be substituted for one another. Take the example above. He stated a logical equivalence between P and not P. He says not P has the very same meaning as P. Therefore, any place you find P, you could put in not P. That's because they are logically equivalent. Material equivalence, however, is simply that they merely happen to have the same truth value. Things are materially equivalent if they have the same truth value. That does not mean they can be substituted for one another. Go back to section 3 on page 288, where material equivalence was introduced. Here we have the statement that P is materially equivalent to Q. Now, do they have the same truth value? Yes, in the lines where it's true, they have the same truth value. Does that mean you could put Q any place you find P? No. I mean, that should be rather intuitive to you. However, if P is materially equivalent to not P, or is logically equivalent, so that there's only true values in that row, then you could substitute them anywhere. But because in material equivalence you don't have all truths in the row, that is, you don't have a logical truth or logical equivalence, you can't automatically substitute one for the other. Is that clear enough? So we have material equivalence, well, we have tautology, material equivalence, and then logical equivalence. And now De Morgan's theorems. Two logical equivalences, which are particularly important, express the interrelations among conjunction, disjunction, and negation. Now, he's going to tell you something a little bit more about these elementary notions that we've been introduced to today. The interrelations between and, or, and negation, not. And what De Morgan's theorems give us are tautological biconditionals. Tautological biconditionals. Now, since in a logical equivalence you can substitute one for the other anywhere because they have the same meaning, De Morgan's theorems are therefore helpful because they give us something that can be substituted, a form that can be substituted for another form because they are logically equivalent. The statement of De Morgan's theorems is found on the page of, top of page 290. And what it says is the negation of the disjunction of two statements is logically equivalent to the conjunction of the negations of the two statements. So let's just go slowly here so you see how this works. If you have the disjunction of two statements, that's going to be P or Q. So we're dealing here with the negation of P or Q. He says the negation of the disjunction is logically equivalent. Notice I use the 3 lines for logical equivalence. Well, it's a material equivalent that is tautological. The negation of the disjunction of two statements is logically equivalent to the conjunction of the negations of the two statements. So let's negate the two statements. Not P conjoined with not Q. Okay. Now, because we understand what logical equivalence is, whenever you see something, two things on the sides of this triple line of equivalence, meaning logical equivalence, this right here, the not parentheses P or Q, can be substituted anywhere for the not P and not Q, and vice versa. because they are logically equivalent statements. And then he says, then there's another aspect of this, the negation of the conjunction of two statements. The negation of the conjunction of two statements. So here we have P and Q being negated is logically equivalent to the disjunction of the negation of the two statements. That is the same as saying not P or not Q. And then in section 6, what we have is a couple of different ways to abbreviate if P then Q. As we know the meaning of if P then Q, that is, we know what material equivalence means, it turns out that if P then Q is the same as saying you don't have a case, that is, you negate the following combination, P and not Q. If you had P and not Q in the case of if P then Q, you'd have a true premise and a false conclusion. And so we don't want that. We negate then that combination. So then, let me state this in notation for those who are listening by tape. Not parentheses P and not Q parentheses is logically equivalent, the three-line equivalent, to if P then Q. I think everyone can see that, can't they? That is just a statement of the meaning of if P then Q. You cannot have a situation where P is true and Q is false. Now that can be simplified even further as you have either not P or Q. Logically equivalent to if P then Q. Now, I've already taught you this because I gave you a little shortcut for testing if P then Q compounds for their truth value. Right? I said, if P is false, you know, anything follows from it, so the compound will be true. And that's what you have here when you have the negation of P in the formula or in the compound, not P or Q, and there's one of the possibilities. If P is false, then you know that if P then Q will be true. On the other hand, if P is true, then it will have to be the case that Q is true. So either P is false or Q will have to be true. And so now what you have here are two different ways of noting this statement, if P then Q. Y'all understand logical equivalence then? Anywhere in an assignment or a problem where you find if P then Q, you may write in its place not P or Q, or you may write in its place not the conjunction of P and not Q. These are all equivalent expressions and therefore are substitutable for each other. All right, let's look at some exercises to put this new information to test. On page 291, Roman numeral 1, Kofi says, for each statement in the left-hand column, indicate which, if any, of the statement forms in the right-hand column have the given statement as a substitution instance, and indicate which, if any, is the specific form of the given statement. Now, it will be helpful so that we don't get confused, which is easy for me to do here, if we remember that a variable, that is one of those lowercase letters, can stand for a compound statement. So if you have a statement like, if A, then B, the sort of thing that might be bracketed as a unit, that compound can take a single variable as its representation, but you can't go the other direction. You cannot take a simple statement, that is just an A or a B or something, and have a compound of variables represent it. Okay, so anything in your statement which can be bracketed together, even though it's a compound, can take a single variable. But you cannot move the other direction. You cannot take a simple statement and turn it into a compound of variables. Now, if you will follow that rule, I think we can make sense of these exercises and the way they're to be done. So let's begin with number one. We have the statement A or B. Of the variables, or of the statement variables we find in the right-hand column, which correspond to A or B?
We'll have C, which is the specific form of number one.
Yes, C does correspond to it, and it does so specifically. It is the specific form. Now, what if we were to make the mistake of being tempted to think, for instance, that F is also a statement form for number one? The reason we'd be tempted is we say, well, there the operative grammar, or the thing that is prominent, is the or. You have if P then Q, or R and S. However, when you have P, Q, R, and S, you have to remember you cannot have that many variables standing for only a simple statement or two. And therefore, this does not prove to be an argument form of which A or B is a substitution. Or it's not a statement form of which A or B would be a substitution. The key here can be found perhaps on page 286, where when he defines a statement form, he says it's a sequence of symbols containing statement variables, such that when statements are substituted for the statement variables, the result is a statement. But here's this qualifying expression: the same statement being substituted for the same statement variable throughout. The same statement substituted for the same statement variable throughout. So back on page 291, if we look at F, here we have statement variables, but that doesn't correspond to A or B because you would not have the same statement substituted for the same variable throughout. You wouldn't have a one-for-one correspondence. Okay, let's try another one of these. Okay, let's try number two, where we have a statement C and not D. Go ahead.
That would correspond with letter D as the specific form?
B as in boy?
No, D as in dog.
D as in dog. That is the specific form.
And could A be the substitution instance?
Yes, I believe that A could be a substitution instance where Q takes not D all the way through, and P would be the same as C. So it has the same form, even though it's not the specific form, because the negation is not there.
Okay.
I'm not claiming that Kofi is altogether clear on this statement and statement form stuff, and so I'll be a little tentative about it. Number three, not E, then parentheses F and G.
Okay, well, if we're going to take the same approach, let's see here. We can use B as well as C.
How could we use C?
Because if we take E, if the opposite of E, then quantity is F and G, and we use the definition of material implication. So that's what I was asking earlier, whether we could do that.
Well, he's only asking us to do the elementary statement and statement form.
Okay, then I would just use B, where P stands for the opposite of E, and G stands for F and G, and it would be a substitution form.
Okay. Now, if we're not allowed to use the negation of a statement to put a variable for that negation, then there wouldn't be any of these forms that fit. And if we are allowed to do that, then the fact is we still don't have the specific form in the case of number 3 found anywhere in the column on the right-hand side of the page. Okay, let's try one more. Number 4. If H, then bracketed I and J. Which of the statement variables on the right-hand side corresponds to that?
I say D. Is that the substitution instance or the specific format? Maybe the specific form is a compound variable can be represented by a single one.
All right, I follow your reasoning. Is there a specific form found?
No.
Okay, let's go to Roman numeral 2. I think this one in Roman numeral 1 is taking too much time. It's not all that important. I think what you do learn here is that a bracketed statement can have a variable stand for it, but you can't have a compound variable represent a simple statement. Number 2, use truth tables to characterize the following statement forms as tautological, tautologous, self-contradictory, or contingent. And let's just take a couple of them. We'll begin with number 1, where we have square bracket P, then parentheses, if P then Q, square bracket, then Q. So we have only 2 variables here, P and Q, and it shouldn't be all that difficult to write the truth table up on the board. So whose turn to it? All right, we have our rows up on the board now. For P and Q, we have the various combinations of truth values. Taking the innermost piece here, if P then Q, you have the various possibilities. Let's examine that. If true, then true is true. If true, then false becomes false. If false, then true becomes true. And if false, then false is a true statement. Now we have to consider if P, then this combination, if P, then Q. So P taken as true, and the combination is true, it would be a true implication. P taken as true, and the compound being false would be a false implication. So far so good. P taken as false has to be true. P taken as false has to be true. Very good. Now we just have one more step. That's to test the total statement. And in the case of the total statement, we have a true implying a false. That is, if P then Q is true, and Q is Q, which is false, so that means it is true. In the third line, we have if P then Q is true, implying Q, which is true, so that's true. And then finally, in the last line, we have if P then Q being a true statement, implying Q, which is a false statement, so it is false. So you filled in the truth table correctly. Why did you call that a contingent statement?
Because in the conclusion, or in the conclusion, we have both true and false statements. If it were to be complete, we had all true answers, we would have a
If you had all truths, it would be tautological.
tautological.
And if you had all falses, you would have
Self-contradictory.
self-contradiction. All right, let's do another one here. Let's take number 4. If P, then bracket, not P, then parentheses Q or not Q.
You want this one on the board?
Yeah, let's put it on the board.
Want me to explain it? Okay. We only have 2 variables here, P and Q. So I wrote down my truth values of P and Q. Then we also have not P and not Q. So in my 3rd and 4th column, I wrote down those truth values.
And they are correct. I can verify that. They're the opposite of the assigned values in P and Q rows.
Now, our 5th column is Q or not Q. And if we look at our 2nd and 4th column, one is true, one is false, therefore that is true. And if we follow that down, they all end up being true. And in our sixth column, we have negative P, or if negative P, then Q or not Q, which, if we look at our third and fifth column,
Let me just note that what you're testing here amounts to the bracketed portion of the statement that we're finally going to be considering.
okay,
Go ahead.
then if we look at our third and fifth column, we see that one is false, and then
You have a false implying a true.
right, and that will always be true.
Okay.
So the answer, no, the consequent is always true. So from there, see?
Yeah, since the consequent is always true, then anything will apply it.
Right.
So everything in that
everything
row
is
will be
true.
true.
And then that is the consequent of
The total statements.
the total statement, which will always, and the consequent will always be true in the total statement. Therefore, everything will be true in the total
So
statement.
every row turns out to be true when we analyze the problem, because the consequent of the if-then statement is always true, as we saw in the row just preceding it. Now, what do we say when every entry in the truth table is true? It's a
Tautologist statement,
apologist statement. What if you had some truths and falses?
then it would have been a contingent statement.
And what if you would have had all falses?
It would have been self-contradictory.
That's right. Let's go to Roman numeral 3 and do a couple of these. Use truth tables to decide which of the following biconditionals are tautologies. Okay, let's remember that a biconditional is the same as material equivalence, and our definition of a logical equivalence is when the material equivalence is a tautology. So number 3 is asking us to determine which of these are logically equivalent. You all understand that? And we're going to do number 2 here, which is parentheses if P then Q being materially equivalent to parentheses not P then not Q. And would you please put that on the board? All right? Number 3. Number 2.
Okay, I took variables P and Q, and
You have all the combinations
All the
of
combinations.
truth values there. Okay.
4 of them, and got the truth value of if P then Q. Then I took the combinations for not P and not Q, there's 4 of those, and got the truth values for not P and not Q. And then
Now wait a minute. Look, you got the truth values for not P then, not
yeah,
Q?
Yes,
Okay.
correct, excuse me, getting ahead of myself there. And then I took those two, if P then Q, and not P then not Q, and I compared those two, and I found that the middle two columns, lines,
Yes, the middle 2 lines.
were false. Therefore, it's not a tautology. It would be a contingent
Okay,
statement.
now the way in which you test a statement of material equivalence is that it is true when you have an equivalent value. So what's being stated as equivalent is the if P then Q, which is in this second row here, or column. Thank you. In this third column, we have if P then Q. Now that's stated to be equivalent to the if not P then not Q, which is your sixth column. So every place where we have a corresponding truth value, the statement of biconditionality, or the statement of equivalence, is true. Every place where we don't have corresponding values, then it's not. So if we go through looking at them, you have true and true, which is going to then be, as a biconditional statement, true. You have false and true, and so that is not equivalent. False is not equal to true, and so you have to put false down here under the statement of equivalence. Do you follow that? The reason why this is false is because this asserts that there's an equivalence between these two things here. But when you compare those two things on the truth table, you find a line where one is false and one is true. So they are not equivalent on that line. You have to put down the statement of equivalence is false. The statement of equivalence is false on the third line for the same reason, whereas the statement of equivalence is true on the fourth line because on that line the two parts of the biconditional are equivalent truth value. So this has been done correctly. That is not illogical truth then. It is a contingent statement. Is it a self-contradiction?
No.
No. Okay, let's do one more before we call it a day here. Number 3. Okay, I've written up on the board the 8 different combinations of truth values for 3 variables, P, Q, and R. Now, one portion of the statement that we are testing here says if P then Q, and so it's easy to determine the truth value of that compound by checking against our columns for P and Q. And so we have if true then true is true, if true then true will be a true statement, if true then false is false, if true then false is false, if false then true is true, and all the rest having false antecedents would mean that the compound will be true. And now we have to test that compound as the antecedent in a further compound statement. If P then Q, then R. So now we're going to test what amounts to the fourth column and the third column. So if we have if true then true, if true then false is false, if false then true, true, if false then false is true, if true then true is true, if true then false is false, if true then true is true, if true then false is false, going through the 8 different rows. Now we have another part of our statement that's being analyzed that says if Q then P. So we have to go through and notice that inference pattern working backwards here. If true then true, be true. If true then true is true. If false then true is true. If false then true is true. If true then false is false. If true then false is false. And then we have the last 2 lines are false antecedents, and so we know that the compound will be true. Okay, then one more part of this biconditional has to be put together. We have the if Q then P as an antecedent to the consequent R. So we're looking at this row, the if Q then P row, to get one set of truth values, and they are said to imply the set over here in column R under the variable R. So we have if true then true is true. If true then false, false. Line 3, if true then true is true. Line 4, if true then false, the compound becomes false. Line 5, if false then true is true. Line 6, if false then false, it's a true compound. If true then true is a true compound, and then finally if true then false, it's a false compound. Now the only thing that remains for us to do is to check the biconditional itself. Number 3 says, if P then Q as one compound, therefore R, is equivalent to if Q then P then R. So we'll take the columns that have these 2. The first one, if P then Q then R, is right here, which is the 5th column. And then the last one, if Q then P then R, is the 7th. And since what we are testing is the statement of equivalence between 5 and 7, columns 5 and 7, we have to go through and check to see if they are equivalent. They are equivalent in line 1. They are equivalent in line 2. They are equivalent in line 3. They are not equivalent in line 4. They are equivalent in line 5. They are not equivalent in line 6. They are equivalent in line 7. and they are equivalent to line 8. So we do have two lines where this biconditional, this assertion of an equivalence, is false. Consequently, we do not have a logical truth here. We have a contingent statement. Have any questions about how we've done that? And let's finish this chapter by taking note of section 8.7. We've already looked at 8.6. These two pages, pages 293 and 294, have some value for us in terms of the history of logic and also an analysis of what logic is all about. Sometimes you'll have people say, well, the most important thing about logic are the three laws of thought: the law of identity, the law of contradiction, and the law of excluded middle. In fact, every once in a while when I go out and I talk about how the Christian worldview is necessary for laws of logic, and have people who do not understand what that claim is all about, we'll try to get into, well, what laws of logic are you talking about? And then I'll say, well, any laws of logic. For there to be laws of logic, you need the Christian worldview. But then they'll say, okay, well now, the most important laws of logic are, and then they'll say identity, contradiction, and excluded middle. It's taken for granted by many people that that's really what logic is all about. That's what it comes down to, these three most primitive laws of logic. Your author now addresses that. He could have excluded these two pages and just gone on and finished his book. But there are always going to be people who say, well, what happens to those traditional three laws? Why aren't they discussed in the book? He says, those who have defined logic as the science of the laws of thought have often gone on to assert that there are exactly three fundamental or basic laws of thought necessary and sufficient for thinking to follow if it were to be correct. If the principle of identity says if any statement is true, then it is true. The principle of contradiction asserts that no statement can be both true and false. The principle of excluded middle asserts that any statement is either true or false. And then he gives the way in which that could be stated in notation. The principle of identity comes down to if P, then P. The principle of contradiction is P and not P is false, or if you will, the negation of P and not P. And then the principle of excluded middle is P or not P. Now, in the history of thought, in the history of philosophy, objections have been made to these principles from time to time, but your author says he doesn't think these objections are all that strong. My personal feeling is he makes too quick a dismissal of these objections, especially with respect to excluded middle. But that's okay, we'll go on. There are debates that have raged through the history of philosophy, even about these three most fundamental laws of thought. He says that you can rescue the laws of thought, however, if you make certain qualifications. For instance, challenges to the law of identity, A is A, that say, well, now wait a minute, things are always changing, so you can't say A is A. Your author says, those statements whose truth values change with time are elliptical, or if you will, incomplete formulations of propositions that do not change. Instead of saying A is A, you could fully carry this out by saying A at T1 is A at T1, where T stands for some temporal designation. With respect to the principle of contradiction, which is, I think, the easiest to defend of the three, nevertheless, Hegelians, general semanticists, and Marxists have attacked it, saying that there are conflicting forces in the real world. And what your author says here, well, we shouldn't call conflicting forces contradictions. But then, of course, within a certain person's worldview, they may choose to use the term contradiction and try to draw certain analogies to logic and all that. Your author simply says, in my system of semantics and logic, I have a way of dealing with that. I don't call those contradictions. Then finally, the principle of excluded middle, page 294, has been the object of more attacks than either of the other principles. It has been urged that its acceptance leads to a two-valued orientation. And that certainly is true. It does lead to a two-valued orientation. And much of what we talk about in life is not two-valued. Is it raining or is it not raining? Well, sometimes it's misting. So which is it? Rain or not rain? An example that is common that he gives is that something is white or it's black. He says, although the statement this is black cannot be jointly true along with the statement this is white, one is not the denial or contradictory of the other. In common parlance, you would think black and white are the contradictions of each other. But your author correctly says, in a sense, white is the opposite of not white. And not white could be any number of things, black, green, red, and so forth. So he says, if we had completely unambiguous and perfectly precise terms, then you could use the principle of excluded middle, that it would be perfectly true. Of course, that all depends on having a way to have exactly precise terms that everyone will agree to. Okay, so your author starts off by saying these three laws of thought have been criticized, but in every case I think they could be defended. I think we could find a way to rescue those three laws of thought. However, in the middle of page 294, although the three principles are true, it may be doubted that they have the privileged and fundamental status traditionally assigned them. As a matter of fact, he says, there are other laws of thought which are much more fruitful for purposes of deduction and hence more important than the three laws of thought. In the last paragraph on the page, he says that the tautologies that he's going to be using to guide the method of deduction are actually more powerful, more efficient, more fruitful, however you want to put it, and therefore more important than the three laws of thought. In a certain sense, you could say, with the three laws of thought, you can't go any further than that. You can't develop a logic from the three laws of thought, because you don't have any and, or, if, then combinations or definitions from the three laws of thought. And yet, as Copey points out, this is the last line of the paragraph before the last one on the page. He says, the three laws of thought can be regarded as the basic principles governing the construction of truth tables. It is certainly the case that you couldn't construct a truth table like we have up here if T didn't stand for T throughout and F stand for F. That's the principle of identity. You couldn't figure out how to do the rows if you didn't assume excluded middle and that contradiction is not to be acceptable. So in a sense, he says the three laws of thought are valuable because they are used when we construct the truth table. But if you don't use the truth table and get definitions for and, or, if, then, you're not going to have a very powerful logical calculus at all. Okay, as we conclude chapter 8, what we have found is that we can test the validity of argument in symbolic logic by the truth tables. That is one method of testing. Let's go back to categorical syllogisms. You remember, after we learned what categorical syllogisms were, we said there are various ways of testing them. One, by logical analogy. Two, by Venn diagrams, which we didn't learn. And three, by certain rules. Now we're dealing not with categorical syllogism, but with propositional logic, and, or, if, then. And he says, you've now learned method one for testing them, the truth tables. But at the beginning of chapter 9, he says, the truth tables in practice grow unwieldy as the number of component statements increases. You notice that even as we went through the very simple exercises, now we've got a whole board full. And this is not the most complicated you could have. You could have other brackets and compound statements. So in practice, the truth tables become very unwieldy. A more efficient method of establishing the validity of an extended argument is to deduce its conclusion from its premises by a sequence of elementary arguments, each of which is known to be valid. Back under categorical syllogisms, go back a couple of days here, we found that we could test the validity of a categorical syllogism by a Venn diagram, although we didn't take the time to learn that. But the Venn diagrams become rather complicated. And so what we did is we learned certain rules for testing syllogisms. In a similar way, analogous to this, we're now going to learn certain rules of deduction by which we can test the validity of an argument without having to go through the unwieldy process of constructing a truth table. And that's what chapter 9 is all about then, turning from truth table testing of validity to the method of deduction as a way of testing validity or invalidity. And so I'd like you to be prepared for chapter 9 tomorrow as we meet again.